Alright, so this chapter is on photons and matter waves. It's the beginnings of quantum mechanics. But I want to begin with a thermo idea. You remember that before we talked about black body radiation, and we knew that things radiated more as they got hotter. What we didn't talk about was the spectrum of that radiation, because we hadn't learned anything about spectrums. If we actually experimentally look at the spectrum of black body radiation, then as it gets hotter, it shifts to the radiation gets greater and greater, as we saw before. Remember, before we learned that the power was equal to sigma, which was a constant, E, the emissivity, area times temperature to the fourth. So we expect more total intensity as the temperature increases. But also, it shifts to shorter and shorter wavelengths for the peak of the energy. So at a lower temperature, 3000 kelvins, the peak wavelength is a little outside of the visible, and it becomes further and further into the visible as we get hotter towards 5000 kelvins. This picture here is the same thing, but instead of being plotted intensity against wavelength, it's plotted as intensity against frequency. This time, because frequency is inversely related to wavelength, as it gets hotter, the peak will shift over to the right instead of to the left. Now this looks very similar to what we saw in the chapters on thermodynamics about the typical distribution of speeds for particles at some given temperature. We had a roughly bell-shaped curve, and at lower temperatures it peaked at lower speeds, at higher temperatures it peaked at higher speeds. Here, instead of speeds, it peaks at a higher frequency or smaller wavelength for higher temperatures. Now we could try and follow the same basic reasoning that we used to get this formula to understand the curve for radiation. But there are some problems. The first part of this formula translates to radiation very nicely. Remember, we said that the distribution of velocities was proportional to the velocity squared, because for higher velocities there were more different directions in which this arrow could point. Well, by the same notion, for higher frequencies or smaller wavelengths, there are more different ways to fit those waves within a confined area. So we expect the intensity as a function of the frequency. I'm using this nu instead of an f for frequency. As a function of frequency and temperature to be proportional to frequency squared or 1 over the wavelength squared. Now if I just use that, I get this idea known as the Rayleigh-Jeans law. Notice at long wavelength it fits very nicely. Long wavelength, small frequency. But it doesn't fit well in here, because it says that as we get to shorter and shorter wavelengths, we ought to get more and more energy, because it's easier and easier to fit waves in there. In other words, every object ought to radiate infinite amounts of energy in the ultraviolet. The problem is that we don't have anything taking on this role, the energy divided by the Boltzmann constant times the temperature with a negative exponent. This is what caused us to damp down at high velocities. But for a wave, we would expect to be able to take an arbitrarily small amount of energy. If I can take an arbitrarily small amount of energy, then I don't get this damping. This on top becomes essentially zero. So what Planck did was he said, let's suppose, for no particularly good reason, that the energy of radiation, of light, was absorbed and emitted in units equal to a constant times the frequency. Using that, he would get an exponential damping just like this, and get a form that fit this particular distribution very nicely. The exact formula he got looks like this. Notice this e to the Planck's constant times frequency over kT on the bottom is essentially an e to the negative energy over kT. But the key idea here is that he had to have the energy come in little bundles so that we would get that exponential damping and cut off the energy at high frequency and small wavelength. This also tells us that the peak wavelength is proportional to 1 over the temperature. The maximum wavelength is just B over the temperature, where B is this number, 2.8977 times 10 to the negative 3 Kelvin meters. This is known as Wien's displacement law, and is a fairly simple law for understanding the primary color of blackbody radiation as a function of temperature.